Hey, ladies and gentlemen, we're going to tackle a real big bear today as we're going to get after question number 6 from the 2019 BC exam. This is a BC only topic as we get into series and try to build some Taylor polynomials. And just in case you weren't sure if I was normal or crazy or something or in between, you're going to think I'm crazy because I absolutely love this question. This is one of my favorite series questions of all time. And I wouldn't be shocked if at the end of this video, you had a little deeper appreciation for this question as well. It's a real fun one. And I think there's going to be some nice twists and turns and some real current patterns in this question. So we've been given a graph of f and a portion of f shown above, as well as the line tangent to f at x equals 0. So we've got like this point of tangency right here. And then other selected values are shown in this table. So the nth derivative, so in this case, the second derivative of f evaluated at 0 is equal to 3. The third derivative evaluated at 0 is negative 23 halves. And the fourth derivative evaluated at 0 is 54. And we'll end up using all of those values at some point before it's all said and done. Now, the first thing they want you to do is just a fantastically traditional question is the third degree Taylor polynomial centered at 0. Nothing better than being centered at 0. Always just a little less to right, if nothing else, when they're centered at 0. So in the most general sense possible, I'm thinking let's go P sub 3 of x. And I use a subscript of 3 to denote or indicate that it's a third degree polynomial. And that doesn't guarantee or mean it's going to have 3 terms. It's all about the biggest exponent in that polynomial when I'm all done. And in a general sense, it's going to be the value of f of 0 plus the value of f prime of 0 multiplied by x. Then it's going to be the second derivative of 0 divided by 2 factorial multiplied by x squared. And then the third derivative at 0 over 3 factorial times x cubed. So all I've got to do is plug in my specific values. Now, this is really a fun question. The value of f of 0 isn't in the table. The value of f of 0 is right here on the graph. And so we know that to be a 3. And then the same thing for f prime of 0. That's not in the table yet. It's on this graph. And what you want to do is focus on the slope of this tangent line right here. And you can read just by eyeballing the graph, we've got a really nice slope of negative 2. So we've got minus 2x. Now the second derivative that I need for right here is going to be this 3. So I've got plus 3 halves x squared. And then last but not least, that third derivative is going to be the negative 23 halves divided by 3 factorial or 6 is going to make negative 23 twelfths x cubed. And that's my final answer right there. So let's shimmy on over to part B and see what they got us doing next. They said, hey, first and foremost, let's see if we can come up with the first 3 non-zero terms for e to the x. And this is hopefully something that you've committed to memory. If you haven't memorized the Maclaurin series for e to the x, all you've got to do is take the first 3 derivatives of e to the x, which don't get any easier than that, and evaluate each one of them at 0 and kind of build that polynomial the same way we did in part A. So anyway, but we've memorized that one, hopefully, and we're going to say e to the x is approximately, I'm not using an equal sign in this case. You'll see why here in a second. It's going to be 1 plus x squared over 2. And I guess I could put like a dot, dot, dot to indicate it's going to infinity. If I did use a dot, dot, dot at the end, then I would change my approximation sign to an equal sign. Now we want the second degree polynomial of e to the x multiplied by f. So e to the x multiplied by f of x is going to be, let's see, this e to the x term multiplied by f, and I'm just going to import these first 3 terms. Now, I could import that fourth term as well, but it really is a waste of time or unnecessary because you only need to go to exponents of 2. And so as I start to distribute, let's say I distribute this 1 to these 3 terms over here. I'm going to get 3 minus 2x plus 3 halves x squared. Now this x here, I'm only going to distribute him to the first 2 terms because going to the third term would be unnecessary. The degree would become too high. And then last but not least, take x squared over 2, distribute it to the first term only so that you don't waste any time. Now we're going to combine like terms here. Let's see. I think I'm getting 3 plus x. And then that if I combine all of the x squareds, it's just going to be 1x squared. And I'm going to box this bear up. This is the second degree, because the biggest exponent is 2, second degree polynomial for e to the x times f of x. All right, so we're chugging here. We're chugging. Part C. So the first thing you're going to see me do is basically rewrite this integral where function f is in terms of t, which is kind of weird. But we're basically just taking our answer from part A. Let's see, this real nice bear here. And I'm just going to rewrite it in terms of t. So let's go 3 minus 2t. 3 minus 2t plus 3 halves. Whoops, I didn't even write the t that I was speaking of. Okay. Not the end of the world, but we do want to model and try to demonstrate the best notation we can. And I believe this is 23 over 12t cubed. The integral is with respect to t. So what I'm going to do is I'm going to go through and I'm going to integrate each term. So 3 becomes 3t minus t squared plus 1/2 t cubed minus, let's see, t to the 4th. And that's going to make my denominator a 48. And then I've got bounds from 0 to x. All this means here is I substitute that upper bound in, is I'm substituting the x for the t, or we're replacing all the t's with x. So we're just being real proper here. We're minding our p's and q's, so to speak. Now the good news is the lower bound was a 0, and you really couldn't ask for a better lower bound, because substituting that's just going to produce a whole string of zeros. So that's my h of x function. Now h of 1 is going to be approximately 3 times 1 minus 1 squared plus 1/2 times 1 cubed minus 23/48. And if we go ahead and combine like terms, we're going to get 97 over 48 as our approximation. Okay. Okay, this is going to require a little bit of backtracking. Know how that original table that they gave me for the nth derivative, and we said at some point we're going to use all those values, and up to this point we haven't used that last value, and we're going to have to go back and grab him here in a second. First things first, let's sort out a few things. And why did they say what they've said here in this question? It is known that the Maclaurin series for h converges for all real numbers x. What they're saying there is that this function has an interval, or the series has an interval of convergence from negative infinity to positive infinity. Not a huge deal for us as the student, but it is a big deal for the test writers that they include that. And it's also known that the individual terms are alternating and decrease in absolute value. So they're kind of using the alternating series test to prove that this series converges when x equals 1. Okay, again, it's not a very big deal to us as the student, but it's a big deal to those test writers that they include that. So we're going to use the alternating series error bound. Let's call it timeout right there. What is the alternating series error bound? Well, it basically says your maximum error, the biggest error you could possibly have, worst case scenario, is guaranteed to be less than or equal to the absolute value of the first omitted term, or sometimes I'll say the first neglected term. So who was the first omitted term? Well, when you used h to approximate h of 1, h itself for us was a third degree polynomial. So the first omitted term is going to be the fourth degree term. Now, we haven't created that fourth degree term, so we've got to kind of go back to the beginning and create this term from scratch. So hang with me here. We're going to shimmy, we're going to shimmy, we're going to shimmy. All right. So the next term here would have been the fourth derivative at 0 over 4 factorial times x to the 4th. Whoops, I didn't squeeze in that x to the 4th. Okay, so here, if I wanted to include it, it would have been 54 over 4 factorial, which is 24, x to the 4th. I believe we could probably reduce that a little bit to make the coefficient 27 over 12. Yeah, let's reduce it even more. think 54 and 24 are both divisible by 6, so that's going to make 9 fourths x to the fourth. Okay. Now, that's not the first omitted term as far as a finished product yet. So this was for f. And then what did we do to f in part C? We integrated it, right? So I've got to integrate that term. I'm going to go all the way back. So what we want to do is we're going to take that 9 fourths x to the fourth. We're going to integrate it to get, let's see, 9 20ths x to the fifth. And what I want to do is I want to substitute a 1 into that term to make 9 20ths. So this is my maximum error, and that is less than or equal to 0.45. And in fact, I think they're precisely equal. But it's all about getting that first omitted term. And once you get that first omitted term, substitute the 1. So, man, I feel like error is always a really, really tough concept, whether it's the alternating series error bound or the Lagrange error bound that we use for non-alternating series. And I feel like I could have done a better job explaining part D there. So don't be afraid to jump down in the comments section here. Ask me some questions about part D, and I'll do my best to explain them. And if we have to, we'll just make another video, maybe one that's devoted just entirely to part D here. But I hope that makes a little bit of sense. Just keep remembering first omitted term, and what's that evaluated at 1 in this particular case. So hope you found this problem somewhat enjoyable. I actually really enjoyed this question, and I hope you continue to work hard, and that hard work pays off when you take the exam and you're rewarded with a great score. So ladies and gentlemen, in the meantime, keep tackling big bears, and I will see you soon.